The last lesson for Unit 5 is number 4, solving radical equations. And we need to decide how to define a radical expression and practice how to solve radical equations. So first, how can I define a radical expression? Well, that means that there's a variable in the radical. And I'll go through how to solve radical equations. There are steps to solve. First, we'll isolate the radical expression. Then we need to determine, is the equation solvable? If we decide it is solvable, then we need to raise both sides of the equation to the power of the index. You then simplify and solve for the variable. There's some vocabulary that goes with radical expressions, and I'm going to draw a little sketch here. This symbol is not called a square root symbol. You've probably been calling it a square root symbol for a little while now, but that symbol is actually called a radical. Everything that's under the radical is called the radicand. And the little number that goes out here is the index. When you have a square root, it's blank out there. So we'll make ourselves a note. If no number, assume it's 2. That would make it a square root. Just like we have an invisible 1, we have an invisible 2 with a root. I have a few examples to do with you, and I'm pulling them from your practice problems. I gave you 20 practice problems, and that's kind of a lot. So I'm going to do a few of them with you, just like I would normally do in a self-check answer sheet. So I'm going to work number 3, which is cube root 4y plus 3 equals 5. So first we're going to isolate. See, I do have a radical expression because my variable is inside the radical. It's part of the radicand. So I isolate the radical expression. I'm going to move this 3 over here so that I can have radical expression, equal sign, everything else over here. It'll be equal to 2. Then I need to figure out, is this solvable? Once I'm isolated, I have a cube root. A cube root graph looks like this. Maybe a slightly different shape, but pretty much it looks like this. The domain is all real numbers. The range is all real numbers. So I could pick any x and find a y, or I could pick any y here and have a solution. So yes, it's solvable. All cube roots are solvable. Next, raise to the power of the index. So I'm going to raise both sides of this equation to the third power. The reason I do that is a cube root and a cubic are inverse of each other. So to cancel out this cube root, I raise it to the third power. When I do that, these cancel, and I just get the radicand. 4y equals 2 to the third is 2 times 2 times 2. 2 to the third is 8. And then I solve for the variable. So I will divide by 4. Y equals 2. I can plug this in here and verify that this side of the equation is equal to 5. That's how you can check yourself. So cube root is in the math button, 4. I can do cube root of 4 times 2 plus 3, and that's equal to 5, so you can check yourself. This is number 7 from your practice sheet. We'll solve it the same way, using the same steps, but this one's a square root. So then we have to check and make sure that it's solvable. First, I isolate my expression, so I'll add 2. And I get square root x minus 2 equals 2. Okay, we've isolated. And then I want to know, is it solvable? A square root graph either looks like this or it looks like that. The domain is not all real numbers. The range is not all real numbers. There are some values I could pick that I wouldn't have a graph there. I wouldn't have a solution. For this, that's going to be when this radicand is less than 0, because then I would be taking a square root of a negative number. We talked about that in the fall. This, though, can be solved because it's equal to a positive number. I want to just double check before I continue solving that a square root is equal to a positive number, so that I know I can solve it. This one is, so I continue. Then I raise to the power of the index. It is solvable. Raise to the power of the index is 2. There's an invisible 2 here, I told you, for square root. So I'll raise to the second power. I also raise the 2 to the second power. The square root and the second power cancel each other out, and I get x minus 2 equals 4. And then I solve for the variable. So I add 2. X equals 6. I could plug this into my original equation and verify that this equation is true and that it checks out. The last example I'll do is number 11 on your practice sheet. The first step here is always to isolate, which means I need to have my radical expression by itself on one side of the equal sign. And this appears to be isolated except for this 3. This is 3 times square root 3x minus 1. The only thing I could do to get rid of that 3 would be to divide by 3. If I divide both sides by 3, I'll have a 1/3 on this side of the equation, and that's not better. So I'll leave it like this, and I will say this one's isolated. Then I need to know, can I solve this? I said for a square root problem that it has to be equal to something positive, and both sides of the equation are positive, so I can solve it. Next, I raise it to the power of the index. This is a square root, so my index is 2. So I raise every piece of the equation to the second power. So I do 3 squared, square root 3x minus 1 squared equals square root 2x plus 4 squared. 3 squared is 9. Square root of 3x minus 1 and then squared will be 3x minus 1. I put parentheses here because I'll have to distribute this 9. That's equal to 2x plus 4. 9 times 3 is 27, so I get 27x minus 9 equals 2x plus 4. And I simplify and solve for x. So I get 25x, put the 9 on the other side, equals 13. X equals 13 over 25. Sometimes you get a fraction and that's okay. We can verify that in the calculator. So these are the types of problems you have to work through on lesson 4. Use calculator if you need to. Ask for help if you need if you have questions to ask. Good luck.